Let's talk about some examples of free body diagrams. I think this is a horse. Don't you think? Good. Lobster horse. They're friends. Whee! Cool. So let's start out with a simple example. Let's say that I've got a truck that's just hanging. Yeah, so hanging by a rope. I've got a truck that's hanging by a rope. So let's do a free body diagram example of that. And we want to line ourselves up so we're looking at it from the side like that. So a pretty simple free body diagram to do. This is going to be an example of something that is in static equilibrium. So I know that my forces all have to add up to 0. So I just draw my truck as a dot, and I draw gravity going down like that. And I've also got a rope attached to the truck. So now I've got a tension force going up. I'm going to try to pay attention and make this arrow equal to the length of this arrow. And I've got a force of tension just like that. So there's a truck dangling from a rope. Yep. Let's switch this and let's make it have dynamic equilibrium. So what should we do there? Let's say that instead of the truck just dangling, we're pulling the truck up at a constant speed. Right? So it's hanging in the air still, but this time it's moving up. So we're lifting the truck, we're pulling the truck up, we're moving it at a constant speed. All right? So remember, in any of these situations with equilibrium, what we're trying to say is that the sum of the forces is going to be 0. So in this situation, the dynamic equilibrium when the truck is moving, I've still got gravity pulling down, and I've still got a tension pulling up, and they're still balanced with each other. Wow, it's actually the same free body diagram. Whether the truck is just dangling there, or whether the truck is moving at a constant speed and being pulled up at a constant speed, you still have the same free body diagram. The tension force is going to equal the gravity force, and they're going to balance each other out. So there's an example of static and dynamic equilibrium. Let's do a different situation. What about if we had the horse here, and let's say that the horse is just, I'm going to put it on his side over here. The horse is going to be standing on a ramp just like this. He's going to visit his lobster friend, and his lobster friend is standing up here. So let's draw the horse on a ramp just like this, at an angled ramp. So this is going to be an example of a static equilibrium case. So I'm going to draw the horse as a dot. I'm going to draw gravity going down like this. So this is going to be my force of gravity. I'm going to have a normal force, but remember the word normal actually means perpendicular. So if we look at this surface right here, perpendicular to the surface is actually going off at an angle this way. So I'm going to have my normal force go off at an angle like this, Fn. And I'm actually going to also have some friction, because if there weren't friction, the horse would be sliding down. So the friction is actually going to be pushing up the ramp, preventing the horse from sliding down, right? The friction's pushing up the ramp. And that is going to be in this direction like this. So I'm going to draw F like that. And what we'll see in these free body diagrams is that normal force and friction are almost always perpendicular to each other like that. So here's a situation of static equilibrium where the horse is just hanging out there, right? Now, what I can also do is I can start to break these vectors down into components, and we'll talk about that in class at some point. So it's hard for me to tell exactly how long to draw each of these arrows, but this is kind of a good gauge right there. Okay, let's do a situation where we have not equilibrium. So I'm going to rip this, and I'm going to say a not equilibrium situation. Okay, so this is going to be not equilibrium, crossing equilibrium out. So let's go back to the truck on the rope. Let's say this time that the truck is being pulled up, but we're actually accelerating the truck in the upward direction. So we have a net force that's going in the positive direction right here. We're going to be accelerating it up. So let's draw a free body diagram there. So we have the truck as a dot once again. We're going to have gravity acting down. And this time we're going to draw our tension force bigger than gravity. So this would result in a net force right here. And the net force would be in the upward direction. And this is a not equilibrium situation. I'm trying to X that out. This is not equilibrium because I have a net force. This force is actually bigger than this force, right? Let's do a different situation. Let's say I have a car that's accelerating along a road, we'll make it accelerate to the right. So it's speeding up as it's going to the right. So this is once again going to be a non-equilibrium situation where the truck is going to be speeding up as it's going to the right. Okay, so how are we going to do that? We're going to draw the truck from the side, or the car from the side. Make myself some space down here. So we're not going to draw the road or anything. We're just going to draw the truck as a dot. Of course, we're going to have gravity going down. Gravity going down. We're going to have a normal force going up. Those are going to be balanced because the car is not accelerating in the up and down direction, right? If one of them were bigger, then the truck would be either accelerating up or accelerating down, and that's not happening. We do have something pushing the car this way, and I'm just going to call it the engine force again. So I'm going to draw this over here, and I'm going to say that that is the force of the engine, like that. And then we always have some drag and some friction, so we can either draw those separately or we can put them as one arrow together, and those forces are going to be acting in the left direction. What I'm going to do is, since I said this is a not equilibrium situation, and the car is accelerating to the right, I'm going to make sure that I draw my drag or my friction. I'm just going to label it as friction over here, going to the left, but notice how this vector is smaller than this vector. So I have a net force going in the right direction. That way I know that it's going to be accelerating in the right. Yep. So this is just a couple of examples of how to do some free body diagrams, both when you have equilibrium, either static or dynamic equilibrium, and when you have a not equilibrium situation, when you have some acceleration.